So, welcome friends to this class. This is again we are still continuing the variational approach to optimal control system. In the previous class we have determined the Hamiltonian and the system in the Hamiltonian we can define by these 4 equations. Last is my boundary condition. So, in a given problem my first 3 equation always remain the same, but the final this last equation can change according to the condition of my endpoints. In all the case my initial points are given, but endpoints can vary problem to problem. If we will take the different systems, my first system is the fixed final time and the fixed final state system. We already have been discussed before. So, I am given with T0, xt0, this normally is given. This is my TF point. If I will fix up the end point at xtf, so if variation will take place subjected to the fixed initial point and the fixed final point. Initial point we already are considering for all the cases to be fixed, but as in first case if we will fix up the end point, so what will be the condition? My delta xf will be 0, my delta tf will also be 0. So, these 2 delta tf and delta xf will be 0, this means delta tf is 0, delta xf is 0. So, last equation will not appear in the problem, but tf and the xtf they already are given, that is why they are fixed. So, we are with the final condition. So, this I know the initial condition, I know the final condition, based on this I can solve my first 3 equations. My second case is the free final time, but the fixed final state. The system is free final time means my final state is fixed, so I am given with the T0, x of T0, my x Tf is fixed and Tf is free. So, if this is x star of t, this is Tf, and let us say this is Tf plus delta Tf. So, I can say this is my xt, which is nothing but x star of t plus delta x of t. So, that is my second case, which is the free final time is free and the fixed final state where xtf is free. So, my trajectory can land anywhere in this where xtf remain the fixed. So, in this case if we will see to my final condition, as XTF is specified. So, what I will have? I have delta XF to be 0. So, delta XF will be 0, but so H plus del S by del T. So, what is left? H plus del S by del T, T equal to TF point, delta TF that must be equal to 0, and this delta TF is arbitrary. So, delta TF is arbitrary. So, the coefficient of delta TF is 0. This means H plus del S by del T at T equal to TF point, that will be equal to 0. So, we will have H plus del S by del T at TF point, that will be 0. So, this is my second case. The third case, naturally if we will have the fixed final time and free final state system. So, we have the free final state and fixed time. Again we start with T0, XT0, and this TF is specified. TF is, so TF will be fixed. If this is my X star T, so my trajectory maybe can go anywhere. So, this will be my xt, which is x star t plus delta xt. So, on the TF line my trajectory can terminate. So, in this case naturally my FTF is specified, delta TF will be 0 and the coefficient as delta XF is arbitrary, delta XF is arbitrary. So, the coefficient of delta XF is del S by del X minus lambda prime T equal to 0. So, this coefficient is 0, this means I have a condition lambda TF equal to del S by del X at TF point. So, this will be my boundary condition in that case. If free final time and the free final state free, so T to TF plus delta TF and free final state, so my trajectory can go anywhere. Again the two cases exist here, which we once we have the free final time and the free final state, if both are independent means there is no relation between delta TF and delta XF. So, the coefficient of both will independently will be 0. So, H plus del S by del T will be 0, del S by del X minus lambda star T at TF point, that will also be 0. But there may be the case that free final time and the dependent free final state system. As we have considered before, let us say my trajectory terminate to a curve given by the theta t. So, this means we are considering a case, okay, I have the slide. We are considering the case that my final state is terminating to a curve theta t, which is given by this curve. So, at Tf point I have x of Tf equal to theta of Tf. So, at this point my x Tf is equal to theta of Tf. So, in this case I can approximate delta xf as theta dot of Tf into delta Tf. So, if I'll approximate this, so I have a relation between delta xf and delta Tf. I'll place this value delta xf as theta dot delta Tf in this given relation. So, here Tf and delta xf are related to each other. I am replacing delta xf as theta dot of Tf, and if I will club this, my terminal condition comes out to be h plus del s by del t plus del s by del x minus lambda star t theta dot t delta Tf equal to 0. Delta Tf is arbitrary, so the coefficient of this will be equal to 0 to get my final condition. So, in total we have discussed the 5 type of the system. The first one was the fixed final time and the fixed final state, in which delta Tf and delta Xf both are 0. My second was the free final time and the fixed final state. I have the fixed final state, so delta Xf will be 0. My third case is the fixed final time and free final state system. So, delta Tf will be 0 and the condition we will get it here. The fourth and the fifth case, we have the free final state and the free time, but in the first case both are independent. So, the coefficient of both delta Tf and the delta Xf are independently 0, and if it is dependent by a curve say theta t, then my condition will be h plus del s by del t del s by del x minus lambda t prime theta t equal to 0. So, these endpoint conditions can be utilized if we are solving a problem. So, next we will take up an example and see how we can apply the Hamiltonian approach to solve a optimal control problem. Let first we will define. So, we are given with, consider a plant which is given as x1 dot t as x2 t and x2 dot t as ut. So, our objective is determine optimal ut and xt such that performance index j equal to T0 to Tf u square t dt is minimum. So, our simple problem, we are considering a simple plant x1 t equal to x2 and x2 dot equal to u. Objective, first a optimal u we will find. With the optimal u, we say our state will also be the optimal. So, we are objective is to find the optimal u and optimal x, which will minimize the j. So, this problem we will solve using the Hamiltonian approach. So, define the Hamiltonian. We have V plus lambda prime F. So, in this case if we will see what we have, V equal to integrand here half of u square t f1 is x2t, f2 is ut, and if we will see the terminal cost S xtf tf, as no cost is given. So, this value will be 0. So, based on this value I can define my h, which is nothing but my half u square. So, I am dropping the t plus lambda prime. What is the lambda prime? It is a Lagrangian multiplier. For each condition we will have the one Lagrangian multiplier. So, this is nothing but my lambda 1, lambda 2, or we can say I am defining my lambda as lambda 1, lambda 2. So, my lambda prime is lambda 1, lambda 2, f1, f2, which is nothing but my x2 u. So, I can define my h as half u square plus lambda 1 x2 plus lambda 2 u. So, here this h is defined as this equation. What is my objective? To solve this using these 4 equations. So, my control equation is del h by del u equal to 0. So, first I will find out the control. So, first step I take del h by del u equal to 0. If I will differentiate h with respect to u. So, my first term u is here. So, this is nothing but u, second term is independent of u, third term is plus lambda 2 equal to 0. So, this will give me nothing but u equal to lambda 2. So, t both the side we are dropping out. So, we can say u equal to lambda 2. With the given value of the h, now we write the other equations. So, I keep my this equation with me. So, my second equation is my state equation, which is giving del h by del lambda equal to x dot t. So, x dot t we are taking as del h by del lambda at optimal point. Optimal point means h we are finding at the optimal. So, u is in this case my u is not lambda 2, but this is u equal to minus lambda 2. If I will replace my u in this, so I can write my h star as 1 by 2 u, the optimal value of the u is minus lambda 2. So, minus, so this is nothing but half of lambda square plus lambda 1 x 2 minus lambda 2 into u. So, this is minus lambda square. So, my optimal h is nothing but lambda 1 x 2 minus 1 by 2 lambda 2 square. So, on this, what is my optimal state x? So, x1 dot t is del h by del lambda 1. If I will take this del h by del lambda 1, because x is a vector of x1 and x2. So, this is del h by del lambda 1 is my x1, del h by del lambda 2 is my x2. So, del h by del lambda 1 if I will take, so this is nothing but x2 and x2 dot of t is del h by del lambda 2 at optimal point, and this is in this case minus lambda 2. So, my x1 dot is x2, x2 dot is minus lambda 2. Similarly, now we can go. So, now we write the co-state equation as lambda dot t s minus del h by del x. So, my co-state equation is lambda dot t as minus del h by del x for optimal value. So, what we have to do? So, my optimal h is this. So, del h by del x. So, again lambda is a vector of lambda 1 lambda 2. So, we will write lambda 1 dot t as minus del h by del x 1, lambda 1 del h by del x 1 with respect to x 1. If we will differentiate this, what I will get? There is no x 1 term. So, this is 0. Similarly, we have lambda 2 dot t minus del h by del x 2. What we will get by this? With respect to x 2 we are differentiating. So, we have only the lambda 1. So, this is so lambda 2 t is nothing but lambda 1. So, from the state and the co-state equation, we will have the state equation as x 1 dot as x 2 and x 2 dot as minus lambda 2, which we are getting by these two equations. And the co-state equation lambda 1 dot equal to 0 and lambda 2 dot equal to lambda 1. sorry, we have did a mistake. Del h by del x2 is this is lambda 1 with negative sign. So, this will be minus lambda 1. So, my this equation is nothing but x2 equal to minus lambda 1, because we have missed this negative term initially to represent this. So, now these equations we have to solve simultaneously. How we can solve this equation? So, we take first equation lambda 1 dot equal to 0. So, solution of this as we know. So, this solution gives us lambda 1 t equal to let us say C1, where C1 will be a constant. If lambda 1 t is C1, we have lambda 2 dot as minus lambda 1, which is nothing but C1. So, this means lambda 2 t is minus C1 t plus C2. So, this will be my lambda 2 t. Say from these equations x1 dot is x2, x2 dot is minus lambda 2. So, what we can write? Next equation we can take as x2, which is minus lambda 2 means this is C1 t minus C2. So, this is x2 dot. If I will simplify this, I will get x2 t as, so 1 by 2 C1 t square minus C2 t plus C3. So, this will be my x2 dot, and if I will have next equation is x1 dot as x2, which is 1 by 2 C1 t square minus C2 t plus C3. So, this will give me my x1 t as, just to integrate this, 1 by 6 C1 t cube minus 1 by 2 C2 t square plus C3 t plus C4. So, I have lambda 1 t, lambda 2 t, x2 t, x1 t, and we can note this, these all are my nothing but optimal values, because they are determined on the optimal u. So, next is these equations. These set of equations we got simply by solving the first three equations. Now, to determine the value of all the constants C1, C2, C3, C4, we have to utilize the boundary conditions, and boundary condition will depend what type of the case we will have. Like we will consider one case here, although these conditions can vary. Let us consider the boundary conditions are given as let we are given with x 0 which is nothing but my x 1 0, x 2 0 transpose is equal to 1 2. The another condition is given as let x 1 2 equal to 0 and x 2 2 is free. So, I am given with these conditions like x 1 0 equal to 1, I have x 1 t given here. So, what this equation give me? Say let us give the name equation 1, equation 2, let us say this is 3 and this is 4. So, x 1 0 equal to 1. So, we can have from equation 4 what we will have? X 1 0 equal to 1 and this equal to t equal to 0, nothing but my C 4, this implies C 4 equal to 1. Now, x 2 0 equal to 2, we can take the equation 3 from equation 3 we have because x 2 0 is 2 equal to, in this case t is 0. So, this all will be 0, we are left with the C 3. So, C 3 equal to 2. So, we have evaluated the two constants C 3 and C 4. Now, my another condition here is x 1 2 equal to 0 means T f is fixed and say for x 1 again a fixed condition is given x 1 2 equal to 0. So, again from 4 x 1 2 is 0. So, again we consider the equation for what actually we will have my t equal to 2. So, 0 equal to I am taking the t as 2, C 1 is unknown. So, this is nothing but 8 by 6 C 1 minus t equal to 2 4. So, 2 C 2 t equal to 2 C 3 is 2. So, 4 plus C 4 is 1 plus 5. So, I get the equation as 8 by 6 C 1 minus 2 C 2 plus 5. Again I need one more equation because I cannot find C 1 C 2 from this equation. So, I will use this which is given x 2 2 is free. This means T f is specified and x 2 T f is free. So, which condition I will use? From my case, my condition is I have the fixed final time and the free final state, and that is applicable to my second state for x 2 only, and my condition is lambda T f equal to del s by del x T f. So, I can write lambda T f as del s by, so lambda 2 T f del S by del x2 at t equal to Tf point. As you can see, we have considered the S to be 0. So, this is nothing but this will gives me equal to 0. So, my lambda 2 Tf is 0. This means I will have equation number 2, which will have lambda 2 T as minus C1t plus C2. So, Tf is 2. So, I am writing lambda 2 which is my Tf minus 2 C1 plus C2, and lambda 2 value is nothing but 0. So, 4 equation we have. So, I have this equation number 5, this equation number 6. So, equation 5 and 6 can be solved to find the value of C1 and C2, which gives me solve 5 and 6 to get C1 and C2. So, what actually we are getting? So, this gives me C1 equal to 15 by 8 and C2 equal to 15 by 4. So, now I have all my C1, C2, C3, C4 as C1 equal to 15 by 8, C2 equal to 15 by 4, C3 equal to 2 and C4 equal to 1. So, with this C1, C2, C3, C4 are calculated utilizing the endpoint condition, and now I can represent my all optimal values in terms of the C1, C2, C3 and C4. So, what I will have, my optimal ut was so u star t was minus lambda 2 t, and lambda 2 t is nothing but my minus C1 t plus C2. So, my optimal u is nothing but minus 15 by 8 t plus 15 by 4. And x1 t is given as 1 by 6 C1 t cube minus 1 by 2 C2 t square plus C3 t plus C4. So, I can place this value to get the optimal x1, and similarly optimal x2 is given as 1 by 2 C1 t square minus C2 t plus C3. So, this is my optimal control relation and these are the optimal states. So, this example gives the application of the Hamiltonian approach to determine the optimal control and the optimal states of a given system. Now, depending upon the final conditions, my values of C1, C2, C3, C4 can change. So, different boundary condition can be taken. As we have discussed the 4 cases, we will end up with the different type of the conditions. Like the case 1, 2, 3, 4, these equations can be utilized to determine the coefficients. So, if I will summarize my approach, I have to solve first the control equation to get the optimal control, then get the state and the co-state equation, solve these equation with optimal control value in terms of the C1, C2, C3, C4 or whatever be the constants are there, and these constants can be determined utilizing the initial condition T0 and XT0 as well as the final conditions which may appear in these 5 forms. So, I stop this lecture here, and in the next class we will further see the application of the Hamiltonian approach to determine the general case of a linear control system. Thank you very much.